Welcome friends to my channel Sommo Physics. Now yesterday I discussed about Maxwell's relation, okay, and there I proved the four famous Maxwell's relations, okay. Now on today's lecture I shall discuss about the second topic, that is thermodynamic potentials. That is the lecture 2 of Maxwell's relations chapter. Thermodynamic potentials, okay. So what are thermodynamic potentials and why they are called so? At first we have to find out this answer. What are the thermodynamic potentials? Okay, now there are four type of thermodynamic potentials. These are internal energy U, Helmholtz free energy, that is we can write as capital F, enthalpy capital H, and Gibbs potential. These four are known as the thermodynamic potentials. This is internal energy, this is Helmholtz free energy, this is enthalpy or total heat, and this is the Gibbs free energy. Okay, so these are known as the thermodynamic potentials. Okay, and why they are called so, that we will come. Okay, so why they are called so, I will tell it later. So first thing is that if you write down the combined form of first and second law of thermodynamics, then you can get du plus pdv, this equals to tds. Okay, so what will be du? Du will be tds minus p dv. Okay, now if you consider a process where entropy remains constant and volume remains constant, that is adiabatic isochoric process, think about that process. So for adiabatic isochoric process, adiabatic isochoric process, what happens? Du becomes 0. That means u tends to du is 0, that means u tends to minimum. Okay, so under a certain condition, that is when we assume the process to be adiabatic isochoric process, the internal energy of a system tends to a minimum value. Okay, the internal energy of a system tends to a minimum value. Now from this equation, okay, give it a name, say 1. So from equation 1 we can also write del u del s volume constant. What we can write? Del u del s volume constant. So volume constant means this term is 0, and del u del s volume constant means t. Okay, and what we write? Del u del v s constant. S constant means this term is 0, del u del v is minus p. That we can write. Okay, from this expression. So volume constant means this term is 0, so del u del s will be t, and s constant means this term is 0, del u del v is minus p. So we can easily write this. Now again, du is a perfect differential. Okay, du is perfect differential, that we all know. Du is a perfect differential. So here u is a function of s and v. So the condition of perfect differential is that del to u del s del v, this equals to del to u del v del s. So because here u is a function of s and v, so what we can write from it? This can be written as del del s of del u del v s, this is v, and this is simply del del v of del u del s v, this is s. Okay, Now del u del vs means what? Del u del vs means minus p. So minus del p del s volume constant. This we can write as del u del s means t. So that is del t del p s constant. Okay. So what is this? This is one of thermodynamical relations. This is one of Maxwell's thermodynamical relations. That is TVS, TVS, that is minus PSV, minus PSV. So starting from the concept of thermodynamic potential, we can arrive also at Maxwell's relation. So if we take the rest three, then we also arrive three other Maxwell's relations. So that I check. So by from the concept of internal energy, we can arrive this Maxwell's relation. Now let us take the second example of Helmholtz free energy. Okay, so let us take the second example of Helmholtz free energy. Now, what is Helmholtz free energy? Mathematically, the formula of Helmholtz free energy can be written in this way. If this is what you can say U minus Ts. Mathematical formula of Helmholtz free energy will be F equals to U minus Ts. Okay. So what will be my df? My df will be du minus tds minus sdt, and from the combined law what we get? Du equal to tds minus pdv. So what will be my du minus tds? So minus pdv minus sdt. Okay. So Helmholtz free energy can be written in this way, minus pdv minus sdt. So you can also give a definition of Helmholtz free energy from this. So if you consider isothermal process, then this term becomes 0 and this term represents the work. So clearly Helmholtz free energy is nothing but the represents the work during isothermal process. You can simply say it, because for isothermal process this term is 0 and this term represents the work. So Helmholtz free energy is nothing but the work represents during you can say reversible isothermal process. Okay. So this is the definition. And again, if you choose a certain process that is isochoric isothermal, okay, isochoric isothermal, okay, if you choose this process isochoric isothermal, then df will be 0. So f tends to minimum. So we see that under this specified condition, the Helmholtz free energy tends to become minimum. Okay, so that we can write easily. Now this expression we can write what will be del f del v temperature constant. This will be my minus p, and what will be del f del t volume constant. This simply minus s. That we can write del f del v temperature constant, this is equals to minus p, and del f del t volume constant, this is equal to minus s. Okay, this we can write. So since f is a perfect differential, so we can write here del 2f by del v del t del v del t. Okay, since f is a perfect differential, what we can write? We can write del 2f del v del t, this equals to del 2f say del t del v. Okay, now I write here, this you can write as del del v of, that is del F del T volume constant T, and this can be write as del T of del F del V temperature constant V. Okay, so what will be my del F del T volume constant? That is minus S. So this is minus S del S del V temperature constant, and this is equals to what is my del F del V temperature constant minus P. Okay, so minus del P del T volume constant. So minus minus cancel. So starting from the concept of Helmholtz free energy, we arrived at the second relation. Okay, we arrived at the second relation, that is this. You can say P S T V. So SVT that is PTV. Okay, so starting from the concept of Helmholtz free energy, we arrived at another relation. Okay, now remaining two I will show you in next class, because the marker pen is almost uh, not working, so I have to buy a new one. So this video is up to this. Now in the next video I will show that other two thermodynamic potentials. Starting from other two potentials we can arrive to other relations. Okay, so this lecture is up to this. Okay, thank you.